Hello, everyone. So last time we were looking at first derivative test and second derivative test in order to be able to determine a local maximum and minimum of a function. So let's remind ourselves about this fact. Last time we saw about the definition of critical points, which means the points such that f prime of x equals 0 or f prime of x does not exist. And we used first derivative test and second derivative test to determine whether a given critical point is a local extremum. So let's look at one more example. Let f of x equals 3x to power 5 over 3 minus 15 x to power 2 over 3. Find the local extrema of this function. So first we need to determine the critical points, the points where f prime is equal to 0 or f prime does not exist. So let's first find f prime of x. So f prime of x equals 3 times 5 over 3, x to power 2 over 3, minus 15 times 2 over 3, x to power minus 1 over 3, right? Just use the power rule, which says that derivative of x to power m is mx to power m minus 1. So we use that to find the derivative of x to power 5 over 3 and derivative of x to power 2 over 3. And then if we simplify this, so this is 5x to power 2 over 3 minus 10x to power minus 1 over 3. And this one we can write it as 5x to power 2 over 3 minus 10 over cube root x. Now cube root x, we can use it as a common denominator. Then 5x to power 2 over 3 times x to power 1 over 3 would be x, right? X to power 2 over 3 times x to power 1 over 3 would be x to power 3 over 3, which is x. So 5x minus 10 will be numerator. So we can write this one as 5 times x minus 2 divided by cube root x. This formula, of course, is valid if x is not equal to 0. Because, you have a denominator, cube root x as a denominator, and if x is 0, denominator becomes 0. So this formula is valid for x not equal to 0. And what about at 0? At x equals 0, f prime of 0 does not exist. You can check that limit f of x minus f of 0 over x minus 0 as x approaches to 0 does not exist. So this formula is for x not equal to 0. For x equals 0, at a single point, we know that if you want to check differentiability, we can check this limit. If this limit exists, the function is differentiable. If this limit does not exist, the function is not differentiable. This limit does not exist, therefore the function is not differentiable, or f prime of 0 does not exist. So the critical points Thus the critical points are x equals 0, because f prime of 0 does not exist. And also x equals 2, right? Because if you want f prime, you want f prime to be either 0 or not exist. If it does not exist, then x is 0. If f prime is 0, then that means numerator should be 0, because this is the formula for f prime. So if a fraction is 0, numerator should be 0, and that means x must be equal to 2. F prime of 2 is 0. So now we can use the first derivative test. To determine whether these points are local extrema. So these are the x values, and then we have to write them in the order 0 and then 2 and then f prime here and then f here. So at 2 f prime is 0, at 0 f prime does not exist. Before 0, you can use a test point. And test point, let's say x equals -1, f prime of -1 equals how much? 5 times -1 -2 over cube root -1. So this is a positive number. Positive, negative, positive. So 0, it's not a 0. X equals 0 is not a root or 0 of f prime, but it's a 0 for denominator. So still the sign changes at that point, because at 0, denominator changes the sign. So if denominator changes the sign, the whole fraction also changes the sign, right? So although 0 is not a 0 root for the f prime, still the sign changes at this point. So the function f, original function f, will be increasing here, decreasing, increasing. So 0 will be local maximum, and 2 will be local minimum. X equals 0, local maximum. X equals 2, local minimum. Okay, so here we use the first derivative test in order to determine local extrema. Could we use the second derivative test by any chance here? Second derivative test, there was a condition for it. F double prime of a must exist. If you want to check whether x equals a is local extremum, f double prime of a must exist. But here at 0, even f prime of 0 does not exist. So therefore, f double prime of 0 does not exist for sure either. And so f double prime of 0 does not exist, so we cannot apply second derivative test for x equals 0. For x equals 2, that's okay, we can use it to verify that it's local minimum, but for x equals 0, we cannot. But always, overall, I think first derivative test is a better method, because not only determines local mean and max, it also determines intervals of increasing and decreasing. Okay, because in practice, especially if you want to sketch the graph of a function, you also need intervals of increasing, decreasing, which can be found using first derivative test. Okay, now the next topic that we want to look at is graphing functions, graphing problems. We started this last time because we explained how to sketch the graph of a polynomial. But of course, graphing polynomials is the easiest type of graphing problem. We could be asked to graph different types of functions, such as rational functions or root functions, logarithmic functions, exponential functions, trigonometric functions. So the algorithm or the recipe for sketching all these types of functions is more or less the same, but you have to do lots of practice in order to get used to, how to sketch the graph of a function. So to sketch the graph of a given function, let's say y equals f of x, first find the domain of f, then find the y-intercept, then and x-intercept if possible, of course. Because x-intercept is not always easy or possible to find. X-intercept means the roots of the function. Some functions, of course, is easy to find their roots, but some functions, is very complicated or even impossible to find their roots. But y-intercept, of course, always very easy. Y-intercept means just find f of 0. Y-intercept always easy. X-intercept sometimes doable. If it's doable, of course, find x-intercept as well. X-intercept or x-intercepts. Then find this. Then determine whether there is any symmetry. Using symmetries are always useful to sketch a graph function. Some functions are symmetric respect to y-axis, and those functions are called even functions, right? Some functions are symmetric respect to origin. Those functions are called odd functions. So it's always useful to determine any type of symmetry if we have. And then find f prime of x and find the critical points and use the first derivative test to determine intervals of increasing, decreasing, and local extrema. And what else then? Find so intervals are increasing, decreasing, local extrema. Also, we have to find the asymptotes. Find all asymptotes of the function. So when you say all asymptotes, means horizontal asymptote or vertical asymptote or oblique asymptote. So I'm going to explain to you shortly that some functions, some rational functions have oblique asymptotes, but that just happens in some rare cases. If you have a rational function and you will see if degree of top is 1 more than degree of bottom, then you can have oblique asymptote. But other than that, you have to find horizontal and vertical asymptote. And that's it. And then sketch the graph of function So we don't need, normally we don't need the second derivative or inflection points. You can use second derivative or find inflection points only if the question asks you to do that. Otherwise, you don't need to do that. So use the second derivative and concavity and inflection points only if the question explicitly asks you to do so. All right. So let's start with some rational functions. Last time we saw how to sketch polynomials. So easiest types of function are polynomials. Then we have rational function. Rational function means one polynomial divided by another polynomial. Let's start with a simple type of rational function. Let's say sketch y equals 2x plus 3 divided by x minus 1. Okay. So first we need to find the domain. First, find the domain. For domain, we need, because we have a denominator, we need to make sure that the denominator is not 0, and therefore that gives x not equal to 1. So domain is equal to, or df is equal to r minus 1. For the interval notation, you can write it as minus infinity to 1 union 1 to infinity. So this is for the domain. Then we also need to find y and x intercept, x and y intercept. But if x equals 0, then y will be equal to 3 over minus 1 or minus 3. And if y is equal to 0, so this is y-intercept. And if y is equal to 0, then 2x plus 3 will be 0. That gives x equals minus 3 over 2. So this is x-intercept. Then we need to determine symmetries. Symmetries means you can replace x with minus x and see whether y remains unchanged. So let me write down the recipe. If x goes to minus x and y unchanged, then that gives symmetry respect to y-axis, an even function. And if x changes to minus x, y changes to minus y, then we have symmetry respect to origin. And in that case, the function is called an odd function. Then we have symmetry respect to origin, an odd function. Okay, so in this example, it's neither case holds. So no symmetry. No symmetry respect to origin or y-axis. there might be another type of symmetry. We can figure it out if we want to, but the question is not asking us to find all the symmetries. So just find it, because we are looking for obvious symmetries basically here, either symmetry respect to y-axis or symmetry respect to origin. There could be other symmetries as well, but really don't insist on finding them, because the question is not asking us to find the symmetries. The question is asking us to sketch the graph. So if there is an obvious symmetry, like respect to origin or respect to y-axis, of course we'll use it. Otherwise, we don't have to search for all types of possible symmetries, because that's a different type of problem. And I have to explain a lot more if you want to find all possible symmetries in the given function. So symmetries, so no obvious symmetry. And then let's find f prime of x. What is f prime of x? F prime of x, I have to use the quotient rule, right? So it's 2x plus 3 over x minus 1. So 2x plus 3 derivative times x minus 1 minus 2x plus 3 times x minus 1 derivative divided by x minus 1 the whole squared. So that's going to be 2x minus 2 minus 2x plus 3 divided by x minus 1 the whole squared. So this is going to be minus 5 divided by x minus 1 the whole squared. Okay. So this function, of course, this is true for x not equal to 1, because x equals 1 is not even in the domain of the original function. So, of course, it's not in the domain of f prime either. Okay, so x equals 1. So it's the 0 of, it's not 0 of f prime, but 0 of denominator. So even zeros of denominators are important. Even zeros of denominators are important, because the function may change sign at those points. Because remember, ultimately, we care about the sign of f prime. So f prime changes the sign at zeros of it, and also possibly at zeros of denominator. Although at zeros of denominator, the function is undefined, but the sign changes, right? Could change from positive to negative in denominator. And if the denominator changes the sign, the whole fraction changes the sign. So it's always important to, when you sketch the sign chart, it's always important to list zeros of denominators as well, although the function is undefined at those points. So sign chart. So before sign chart, so do we have any critical point here? Because f prime, critical point means f prime 0 or f prime does not exist. Of course, f prime cannot be 0 because you have a non-zero numerator, which is minus 5. So if numerator cannot be 0, then the whole fraction cannot be 0 either. So f prime of x equals 0 has no solution. F prime of x does not exist, again has no solution. You could say, okay, f prime does not exist at 1, but 1 is not even in the domain of the original function. So when we say critical points must be in the domain of the original function. Note, x equals 1 is not in domain. So is not a critical point. By definition, critical point must be a point of domain. So no critical point here. No critical point. Now let's use the sign chart for f prime. So here we determine the x values and we list the critical points. There is no critical point, but denominator has a 0. We said that in addition to critical points, if denominator becomes 0 at some point, please list them for sign chart for f prime. So at 1, denominator becomes 0, and then f prime here, and then f here. So of course, f and f prime both are undefined at 1. But that's okay. Now let's see before and after what happens. Well, f prime, before and after, look at f prime. It's -5, which is a negative number, divided by x minus 1 the whole squared. X minus 1 the whole squared is always positive, except that 1, which is 0, but we have put 1 apart because we already said it's undefined at 1. But apart from 1, x minus 1 the whole squared is a positive number. -5 is a negative number. Negative over positive is negative. So f prime will be negative before 1 and also after 1. And that means f is decreasing and also decreasing here. Now, what about asymptotes? For vertical asymptotes, we have seen before that if there is a denominator for f, not for f prime. Forget about, for asymptotes, forget about f prime. Just look at the original f. What was f? F of x was 2x minus 3 divided by x minus 1. Now, if x minus 1, if I put x minus 1 equals 0, that gives x equals 1, right? So this is a potential vertical asymptote, but I have to check. I have to check the limit. Check the limit. Limit f of x as x approaches to 1 from left will be limit 2x minus 3 over x minus 1. X approaches to 1 from left. So that's 2 minus 3 divided by 1 minus minus 1. That's minus 1 over 0 minus. And this is plus infinity. X approaches to 1 from left. We get minus 1 over 0 minus. So this is plus infinity. Oh, sorry, it was 2x plus 3. 2x plus 3, the original question. 2x plus 3. So 2 plus 3, 2 plus 3 is plus 5 over 0 minus. So that's minus infinity. See, let me explain why I had a pause here. I knew that there should be something wrong. How did I know that? Because I looked at my sign chart. It's saying that the function is always decreasing. So how come if the function is decreasing, like before 1, it cannot go to plus infinity because you cannot decrease to plus infinity. If a function is always decreasing before 1, it cannot go to plus infinity. It can go to minus infinity. So that's why I was doubtful about this plus infinity that I got in the beginning. That's why I realized that there should be some calculational mistake. And then I realized that the function was 2x plus 3 over x minus 1. And I corrected the calculation. So if you always compare all the results that you have, the sign chart, the other calculations, if you check that they are consistent with each other, it's always helpful. In this case, if these two things are not consistent, then you can guess that there should be a calculation mistake and you can correct it. Okay, so left limit is minus infinity. Similarly, you can check that the right limit at 1 is plus infinity. So look at the graph of the function, it decreases all the way before 1, right before 1 goes to minus infinity. Right after 1, the function starts from plus infinity and again decreases. So the function can decrease from positive infinity, that's okay, but it cannot decrease to plus 2 positive. It cannot decrease to positive infinity. It can decrease from positive infinity, of course, that's okay. So we had one vertical asymptote, x equals 1. And what about horizontal asymptotes? So this time we have to check limit f of x as x goes to plus or minus infinity. So this is going to be limit 2x minus 3 over x minus 1. X goes to plus or minus infinity. And if you remember, we can use the technique we used in the first chapter, which was factorizing highest power of x from top and bottom, or we can just simply use L'Hopital. L'Hopital, then this is derivative of top, which is 2, over derivative of bottom, which is 1. X goes to plus minus infinity, this is 2. So we can say that y equals 2 is a horizontal asymptote. Please make sure you write y equals 2 is a horizontal asymptote. Don't say 2 is a horizontal asymptote. Horizontal asymptote must be a horizontal line, and y equals 2 is a horizontal line. Now we are ready to sketch the graph. Now, see, we did all the steps that we explained here. Find all asymptotes and then sketch the graph. We did everything. Now sketching the graph. Sketching the graph. We had two asymptotes. Remember, x equals 1 was our vertical asymptote, and y equals 2 was our horizontal asymptote. And we saw that the function decreases to minus infinity. So it starts from 2. And y-intercept was how much? Y-intercept was minus 3/2. So minus 3/2, let's say here. So 3/2 was x-intercept, I think. Let me check again. Minus 3/2 is x-intercept, minus 3 is y-intercept. Minus 3 is y-intercept. So 1, 2, 3. So the function starts from 2, it's the horizontal asymptote, and minus 3/2 is the x-intercept. Starts from 2. Okay, so the function looks like this here on this branch. And so the function decreases before 1, and right before 1 goes to minus infinity. Decreases before, look at the sign chart, decreases before 1, right before 1 goes to minus infinity. And right after 1 starts from positive infinity. right? After 1 starts from positive infinity and goes all the way to, decreases all the way. And again, at y equals 2, you have a horizontal asymptote. So remember, y equals 2 is horizontal asymptote, whether x goes to plus infinity or x goes to minus infinity. So from minus infinity, we started from y equals 2, we decreased all the way to minus infinity right before 1. Right after 1, we started from positive infinity. Again, we decreased and we approached y equals 2 as x goes to infinity. Y equals 2 is a horizontal asymptote, whether x goes to plus infinity or x goes to minus infinity. Okay, that's it. This is this graph of this simple rational function. Among rational functions, this is considered as a simple one because top and bottom both were linear functions. Now let's look at another example. Sketch the graph of this time, let's say y equals 2x squared, y equals f of x equals 2x squared minus 8 divided by x squared minus 16. So how can we sketch the graph of this function? Well, always look at the function. If it's possible to simplify it, you can simplify it first. I can simplify this function because, I can write it as the solution. First, note that f of x can be written in the following form. Can write f of x, of course, as 2 times x squared minus 16. See, the top is 2x squared minus 8. Basically, I want to do the long division, but I don't want to go into all the process. I can just guess the numbers because they're simple. So 2x squared minus 8 can be written as 2 times x squared minus 16 divided by x squared minus 16. But of course, I need a constant to adjust the constant because 2 times x squared minus 16 with 2x squared minus 32. But here I need minus 8. So if it's minus 32 and I need minus 8, that means I have to add 24, right? So I can add 24. If I add 24 to minus 32, then I'll get minus 8. So then this can be written as 2 plus 24 over x squared minus 16. Right? 2 times x squared minus 16 over x squared minus 16 is 2 plus 24 over x squared minus 16. All right. So this form is a simpler form. It can help us to find the asymptotes faster. So let's see how. But let's start with the domain first. So domain, you don't have to write f of x in this form. If you prefer the original form, you can work with the original form as well. Domain of this function, what is it? I need the denominator to be non-zero. That means x squared not equal to 16. That means x not equal to plus minus 4. So domain equals all real numbers except 4 and minus 4. This is the domain. Then we need x and y intercepts. So for y-intercept, if I replace x with 0, then y will be 2 plus 24 over minus 16. So that's going to be minus 32 plus 24 minus 8 over minus 16. That's 1/2. 1/2 is the y-intercept. For x-intercept, so if I set y equals 0, that gives 2 plus 24 over x squared minus 16 equals 0. And that gives 2 equals 24 over 16. If I take this 24 over x squared minus 16 to the other side, 24 over 16 minus x squared. So 32 minus 2x squared equals 24. And that gives 8 equals 2x squared. X squared equals 4. X equals plus minus 2. These are x-intercepts. And then symmetry. Symmetry, see, if I change x to minus x, look at the formula for f. This is the formula for f. If I change x to minus x, y will not change because 2 will not change, 24 will not change, x squared will not change if I change x to minus x. So y will not change. Y will be unchanged. And that means, we have an even function. Even function, which means symmetric respect to origin, respect to, y-axis. Even function means symmetric respect to y-axis. Now let's find f prime. The next step, find f prime. And critical points. So f prime of x means derivative of 2 plus 24 over x squared minus 16. Derivative of 2, of course, is 0 plus 24 times x squared minus 16 to power minus 1. So I can use chain rule. U to power minus 1 derivative is minus u prime u to power minus 2. X squared minus 16, if I call it u, I have 24 over u. 24 over u, 1 over u derivative, or u to power minus 1 derivative, is m u to power m derivative, m u prime u to power m minus 1. So minus 1 u prime u to power minus 2. So 24 times minus 1 times 1 over x squared minus 16 to power 2 times the derivative u prime times u prime. What is derivative of x squared minus 16? It's 2x. So times 2x here. So this is minus 48x divided by x squared minus 16 to power 2. So if f prime equals 0, that gives minus 48x equals 0. That gives x equals 0, which is my critical point. But remember, we said that when you want to sketch the sign chart for f prime, you have to also include the zeros of denominator as well, although they are not going to be considered as critical points, but still they could have important role in the sign chart because we could have a sign change at those points. So if the denominator is 0, That gives x squared equals 16, x equals plus minus 4. So these are zeros of denominator for f prime. Now let's use the sign chart for f prime. So sign chart for f prime, we have the x values here. We have to list them in the order. I have -4 and 4 and 0. So in the order, I have -4, that's the smallest one, then 0, then 4, and then f prime here, f here. So f prime and f are both undefined at -4 and 4 because these are the zeros of denominator for both f prime and f. And before 0, you can use a test point. Let's say between 0 and -4, I could use -1. And f prime of -1 is how much? -48 times -1 is 48. Divided by 1 minus 16 is -15 the whole squared. This is positive. So positive here, negative here, 0 is a simple root. But 4 and -4, we would not have any sign change at those points because of the power 2 here. Because basically this one can be written as what? X minus 4 times x plus 4, right? But then there's a power 2, so x minus 4 squared times x plus 4 the whole squared, right? So these are repeated roots with multiplicity 2, and there will be no sign change at 4 and -4. So no sign, sign change. So minus remains minus, and here plus remains plus. No sign change at -4 and 4 because they're repeated roots with multiplicity 2 in denominator of f prime. And then f here will be increasing, and then decreasing here, and then decreasing here. So here I have increasing to decreasing. So I have a local max here. And here at -4 and 4, because these are also zeros of denominator of f, I will have vertical asymptotes. So let's check asymptotes next. Asymptotes. So for horizontal asymptote is easy. Limit f of x as x goes to plus minus infinity. This is limit. Remember the simplified version of f of x, we wrote 2 plus, what was it? 2 plus 24 over x squared minus 16, x goes to plus or minus infinity. So as x goes to infinity, x squared minus 16, of course, goes to infinity. 24 over infinity is 0. So this is 2 plus 0, which is 2. So y equals 2 will be my horizontal asymptote. And for vertical asymptote, for vertical asymptotes, we need to find the zeros of denominator for f of x, which is x squared minus 16. So we said x squared minus 16 equals 0. And then we got x equals plus minus 4. So these are basically the potential vertical asymptotes, but we still need to verify whether the limits are actually infinity or minus infinity to confirm that these are actually vertical asymptotes. So the left limit at -4. So let's start with -4. And let's start with the left limit. Left limit at -4. We can calculate it. We replace f of x with the expression we found above. Now, if we replace x with -4 minus, which means left limit from -4. So number x is basically a little bit less than -4 here. Then we get 2 plus 24 over -4 minus 4 is -8. -4 minus plus 4 means a number a little bit less than -4 plus 4. We'll get a number a little bit less than 0, which can be denoted by 0 minus. Now, -8 times 0 minus will be 0 plus, right? Because this number is negative, this number also negative. Product of two negative numbers is positive. So this time this will be a little bit more than 0. This is -8 times a number a little bit less than 0. The whole result will be a little bit more than 0. And 24 over 0 plus will be plus infinity. And 2 plus infinity will be infinity. So left limit at -4 is infinity. And other limits are similar. So this is left limit at -4. Then you can find the right limit at -4 and also left limit and right limit at 4, the other points. And you can, once you find these three limits, you can confirm that these 2 points, x equals -4 and x equals 4, are actually vertical asymptotes. So I summarize these limits in the sign chart here. See, at -4 minus means a little bit less than -4. We just confirmed that the limit is infinity. Similar calculation shows that -4 plus, a little bit after -4, the limit is minus infinity. And for 4, a little bit before, the limit is minus infinity, left limit is minus infinity. A little bit after, right limit is infinity. So now that we have done all these steps, we are ready to sketch the graph. So there you are. We have first of all, of course, we need x and y axis. After you sketch x and y axis, you can sketch the asymptotes. We had two vertical asymptotes, x equals -4 and x equals 4. And we had one horizontal asymptote, y equals 2. And so if you look at the sign chart, before -4, the function increases all the way to infinity. And the asymptote, remember, y equals 2 is the horizontal asymptote, right? At -infinity and also infinity. So when x starts from -infinity, you start with y equals 2, asymptote of y equals 2. A little bit before, basically, a little bit above, basically, y equals 2. And the function increases all the way to infinity right before -4. And the function will be at -infinity right after -4 and increases all the way to 0, all the way to x equals 0. At x equals 0, y value was 1/2. We calculated this above, the y-intercept. See, y equals 1/2. And this is y-intercept. X-intercepts were plus and -2. So we started from 2, right above 2, went all the way to infinity, then -infinity, crossed the x-axis at -2. This value here is -2. And crossed the y-axis at 1/2. Y-intercept is 1/2. Then at 0, we have local maximum, right? The sign chart confirmed this. Local maximum at 0 because increasing before, decreasing after. So at 0, we had local maximum here. Then the function starts to decreases all the way to -infinity right before 4. Right after 4, it starts from infinity, again decreases all the way to y equals 2. And because y equals 2 again is a horizontal asymptote if x goes to infinity. So as x goes to infinity, you will be right above y equals 2. And that's it. So the function increasing is increasing before -4, between -4 and 0, at 0 local maximum, and then decreasing between 0 and 4, and also decreasing between 4 and infinity, and meaning after 4, basically. Well, that's also, this is how we sketch the graph of this function, this rational function.